Greetings everyone, I'm Sreyan Ghosh and I'm going to present a paper titled Cisco AAAI-CAD21 Shared Task, Predicting Emphasis in Presentation Slides using Contextualized Embeddings for the AAAI-CAD21 Shared Task Presentation Slides Emphasis Selection. This work was a collaboration with collaborators from Cisco Systems, Midas at IIIT, and Christ deemed to be University. My other co-authors for this paper are Sonal Kumar from Christ deemed to be University, Jalan, Hemant Yadav, and Dr. Rajiv Ratn Shah from Midas at IIIT. A brief introduction about the task and its objectives. Presentation slides have become quite common in workplace scenarios, and researchers have previously developed resources that guide presenters on the aspects of overall style, color, and font sizes to ensure that the graphical representation of the slide creates an impact on the viewer's mind, and the viewer can relate and understand the message that the presenter is trying to relay through the slide. This shared task aims at designing automated approaches to predict which word in the slide should be emphasized on, for example, making bold or italics to improve the visual appeal of the slide. In figure 1, we can see how emphasized text in presentation slides on the right hand side is much more visually appealing and creates a better impact on the readers than the non-emphasized example on the left. Now we'll talk a little about the dataset. In table 1, we can see the annotation scheme followed by the annotators of the dataset. They followed the very conventional bio-tagging scheme where each B stands for the beginning of the emphasized span, I stands for the intermediate words, and O for the non-emphasized words. Thus, every word to be emphasized was either tagged as a B or an I by the annotators, and the final emphasis score was calculated using the average scores of all the 8 annotators. The dataset primarily had instances of slides, which in turn had a number of sentences in them, which in turn had a number of tokens in them. In table 2, we can see quick statistics as to what were the total number of slides in the train, dev, and test sets, the total number of sentences, and the total number of tokens in the train, dev, and test sets. In table 3, we can see the length of the the average, min, and max length of the instances which were the slides in the train, dev, and test sets. As we can see, the minimum length of the slides ranged between 13 to 180 with an average length of 78 in the train set. Statistics about the dev and test can also be seen in table 3. Now the evaluation metric which we will be using. We use math score provided to us by the organizers of the competition or the shared task for evaluation of all our approaches. The formula used for the same can be found in figure 2 on this slide. For this specific task, the organizers decided to take the final score as the average of the math scores for values of m corresponding to 1, 5, and 10. Now trying to dig a bit deeper into the dataset to find token level features that could enhance the performance of our models. One very interesting observation we found is most of the words with an average emphasis score of more than or equal to 0.5 was very commonly classified as scientific key phrases in NLP research literature. This is very clearly evident from figure 3, which is a word cloud of all the tokens with an emphasis probability of more than or equal to 0.5. Thus, what we did with this is we used a sequence tagging model with bio-tagging scheme trained on scientific key phrases to extract such words from our dataset and use them to enhance performance in one of our two approaches. We refer to this feature as the key phrase feature throughout our paper. With table 4, it is also very clearly evident that our key phrase feature has the highest average emphasis scores across tokens in training and development set among all the other distinct token level features that we have explored in the dataset. Now, coming to our approach towards the problem, we treat this problem as a sequence labeling task where, given a slide and its tokens, we tag each token in a slide with the degree of emphasis that needs to be laid on this token, ranging between 0 and 1. Our first approach, the BiLSTMELMo approach, is inspired by the baseline paper for this task, where we extract the Elmo embeddings for each word in a sequence, and additionally, we pass the input through a character level BiLSTM network where the combined forward and backward embedding for the last character of each word is then passed through a highway layer, which effectively provides us with the contextual word level embeddings for the entire sentence. These embeddings are then concatenated with the extracted Elmo embeddings and input to the BiLSTM layer, followed by an attention layer. The output of the attention layer is then concatenated with the POS tags and the key phrase feature for the corresponding word at each time step. Now, combined, the attention output and the external features are fed to a time-distributed dense layer, followed by a time-distributed output layer. We use either sigmoid or softmax for a final output layer, depending on whether we used binary cross entropy loss or KL divergence loss for label distributed learning, which we also explore as part of our training process. Second, our transformer approach makes use of one of the two transformer architectures, that is either XLNet or RoBERTa. First, the tokenized word input is passed through the transformer architecture, and the outputs of all the encoding layers of the transformer are concatenated together to get the final embedding E for any given word. This embedding is now fed through a BiLSTM layer, followed by a set of time distributed dense layers. Finally, the output for each time distributed dense layer are fed to a time distributed output layer. Similar to a previous approach, we use either sigmoid or softmax depending on whether we use binary cross entropy loss or KL divergence loss for label distributed learning. So, coming to the results. Table 5 shows the performance of all our individual models. XLNet trained on binary cross entropy loss proved as the best performing single model for us. An ensemble of this model and RoBERTa transformers approach trained on label distributed learning proved as our best submission in the evaluation phase with a score of 0.518. Second, an ensemble of XLNet with BiLSTMELMo model trained on label distributed learning proved as our best performing model in the post-evaluation leaderboard with a score of 0.543. Additionally, we also divide the slides into its individual sentences and evaluate all our approaches on the math score where M belongs to 1, 2 and 3 because we deemed these values of M to be fit for smaller sentences. XLNet outperforms all our models with this approach too. Additionally, we have also provided a detailed analysis of our results and predictions in our paper. Figure 6 shows the emphasis heat map analysis of our predictions, which correspond to ground truth, BiLSTMELMo model, XLNet model, and best ensemble model respectively from top to bottom. All the models for all the approaches that are showed in this heat map were the best performing models from both these approaches, BiLSTMELMo and XLNet. Table 8 shows an analysis of POS tags versus the average emphasis scores for our best performing BiLSTM model and transformer model, which is the XLNet model. One interesting observation we can see in table 9 is the performance of our best performing model fails with the increasing length of the slides. So now the conclusion and our future work. In this presentation and our paper, we present our approach to AAAI CAD21 Shared Task, predicting emphasis in presentation slides. Our best submissions gave us a math score of 0.518, placing us third on the evaluation phase leaderboard, and a math score of 0.543, placing us first on the post-evaluation leaderboard at the time of writing the paper. Future work includes using a hierarchical approach to emphasis prediction as a sequence labeling task using both sentence level and slide level representations of a word. Additionally, we have made all our datasets and our code public, which can be found on the GitHub repository, the link to which has been provided at the bottom of this slide. Finally, I would like to thank all my co-authors without whom this work wouldn't have been possible. I would also like to thank the organizers of CAD21 workshop at AAAI21 for organizing a great shared task. Thank you.